Even the most stable structures are bound by the laws of gravity. At the critical point of impact, an order yields to irreversible chaos.
Time moves in one direction. But the laws of physics are reversible.
Even the most rigid structures give way. Hydrogen bonds relax, transitioning from solid to liquid. A beautiful, inevitable shift. Even the strongest materials cannot hold on to heat forever. At the atomic scale, energy actively bleeds into the cold, leaving it perfectly cooled. Time moves in only one direction. Once done, these processes cannot be reversed. It is the fundamental law of disorder. Deep within this microscopic world, particles drift and collide in a state of constant, random motion. By reversing every particle velocity exactly, they retrace their paths back to the start. In classical mechanics, motion is perfectly reversible. The laws of physics do not distinguish between past and future. At the quantum level, the laws of physics are perfectly reversible. Here, time's arrow loses its direction. Under the idealized laws of Newtonian dynamics, orbital motion is perfectly reversible. By reversing the vector, time itself appears to run backward. Why does time flow forward? Is reality an illusion? Most fundamental laws are time-symmetric. But rare interactions break this rule.
Under ideal conditions, the laws of physics are time reversible. By reversing every velocity, the system perfectly retraces its own history.
From just 10 isolated particles, we pull back to reveal millions more, creating a single physical droplet. When particles move in vast numbers, individual paths no longer matter. Temperature redefines the chaotic swarm into a single unified texture. An isolated system will always move toward a state of maximum disorder. This fundamental law governs the entire cosmos. Release the barrier, and a fundamental law of the universe unfolds. Driven by pure chance, they spread evenly. This is diffusion in its purest form. To understand the system, we must look at its microstate. Every position and momentum is frozen. Highly concentrated states have very few compatible microstates. But as gas distributes, the number of possibilities becomes vastly larger. Macroscopically, these four systems appear identical. Yet, the precise arrangement of particles is unique. Let's track four distinct particles. By moving one, we create a new arrangement. A 2 and 2 split is the most likely outcome. To understand the macroscopic world, we must bridge the gap from a few particles to Avogadro's scale of 10 to the 23rd. This is where matter truly begins. Some macrostates are highly restrictive, compatible with only a few arrangements. To create local order and decrease entropy, a system must expel heat to its surroundings. We tend to associate entropy with mere disorder, but it is truly a matter of statistical probability. Even in perfect equilibrium, random motions can create spontaneous shifts, but without intervention, they quickly disappear. Within this nanoscale environment, particles move in purely random trajectories, creating brief, spontaneous clusters before dispersing. To understand the system, we must look closer. Removing the individual labels reveals a coarser view. Now, the overall density distribution defines the state. In a perfect reversal of thermodynamic flow, dispersed particles begin to reassemble. Imagine if we could simply reverse the flow of time. Every diffused scent returns to its source, defying entropy. At the microscopic level, we see the first signs of order. They follow precise trajectories, yet they never truly assemble. Within this vast configuration space, a single narrow pathway emerges, the only route to total reconstruction. When we look at shattered glass, we see an irreversible arrow of time. But by mapping every physical trajectory, we can trace its chaotic journey backward. From a few stray atoms, clusters begin to form, multiplying into the billions, until order emerges from the chaos.
At the interface, energy transfers, moving from the hotter block to the colder one.
When two objects at different temperatures meet, a silent dance of microscopic energy begins, flowing until they reach a perfect balance. At the microscopic level, heat is simply motion. Fast-moving particles collide with slower ones, transferring energy. While energy moves both ways, the net flow is always to the cold side. Let's compare two distinct particle systems. In the cooler system, velocities cluster narrowly, but as energy increases, the distribution broadens, revealing the chaotic motion of heat. When hot and cold materials meet, their temperatures slowly converge until the boundary disappears. At thermal equilibrium, the energy exchange is perfectly balanced. Energy naturally disperses, flowing from hot to cold. This fundamental arrow of time is strictly irreversible, driving the entire universe toward a final, perfect balance. All systems in the universe share a single, inevitable fate. They move from order to complete and utter chaos. This is the law of entropy. In a low entropy state, fewer configurations are possible. But as disorder increases, multiplicity creates vast landscapes of chance. It seems counterintuitive, but a refrigerator doesn't actually add cold. It removes heat. Energy spontaneously disperses, moving always toward equilibrium.
Every fleeting impression leaves a mark in time, preserved in stone, bridging millions of years.
When weight is applied, the sand behaves like a liquid. Water is forced out from between the grains. As the foot lifts, suction pulls water back in. Every second, countless rays of light carry information. Bending through precision glass, they converge to reveal the world in perfect detail. From the alignment of a magnetic field to the precise charge in a silicon cell, from the raw texture of ink on paper to the microscopic pits read by a laser. Inside the living brain, billions of neurons form a vast, intricate web. Electrical impulses travel swiftly along these pathways, strengthening connections and physically reshaping the network. Every bit of data processed leaves a physical footprint, from the active firing of our own neurons to the magnetic drives of our vast networks. Information always generates heat. Memory is not a perfect record of the past. It is a landscape shaped as much by what remains as by what has been lost. Every human step leaves a trace, a subtle ripple in the fabric of time. To test the limits of Einstein's reality, we must separate time itself. But perfectly synchronized clocks cannot stay identical forever.
These two atomic clocks are perfectly synchronized. Now, one will remain stationary, while the other begins its journey through space-time.
Clock A remains stationary, while clock B begins its high-speed journey. Trajectories through space-time part, revealing the true nature of time. When stationary, the pulse moves vertically. But when moving, its path traces a longer, diagonal line. For a moving clock, time itself slows down. The faster it travels, the slower it ticks relative to an observer at rest. Having followed different paths through space and time, both clocks still tick with perfect local precision. Yet their gathered readings now differ. At the velocity of light, time slows down. Precise atomic clocks reveal this hidden truth. Gravity bends the very fabric of reality. According to Einstein, gravity shifts the very flow of time, ticking faster in the vast emptiness of space.
Deep within gravity, time flows slower relative to the stars.
To match the perfect precision of earthly clocks, GPS satellites must adjust for the flow of time.
Time flows in two distinct ways, through the relentless increase of entropy and through the warped fabric of relativity. Both define the reality of our universe.
Approaching the event horizon, space and time begin to lose all meaning. Here, light itself is bent by gravity. In the deep universe, time is not absolute. Near a black hole, gravity stretches time itself, slowing its flow relative to the cosmos. According to Einstein, time is not absolute. The further you are from a massive object, the faster time passes. As the probe approaches the event horizon, Einstein predicts a strange distortion. Its light shifts to a deep, frozen red. As the probe approaches the event horizon, its internal clock continues to tick normally. The threshold is crossed without a sound. As matter falls in, the event horizon grows. Its surface area reveals the total entropy within. Outside a black hole, light can still escape, but at the event horizon, the paths of light tip inward. Inside, every path bends backward toward the center. At the very edge of a black hole, space is never truly empty. Here, quantum fields produce a faint thermal glow known as Hawking radiation. As the probe approaches the event horizon, extreme gravity warps its light, leaving only mass, charge, and spin. Over eons, even giants fade, evaporating into a stream of quantum particles, leaving behind only pure information.
Information is not identical to energy. It can be expressed by a magnetic flip, a flow of electrons, or even a strand of DNA. The message remains the same.
In a reversible system, every input has a unique output. By conserving information, we can trace the logic backward. To reset a bit, we must make two possibilities converge. Irreversible operations demand a physical alignment. Here, both 1 and 0 flow into a single path, leaving the system at 0. Every logical reset releases a precise amount of heat. This is Landauer's limit, manifesting as EEK/BT ln2. Information takes many physical forms, from the digital grids of a silicon sensor to the raw tactile chemistry of ink on paper, flashing through the brain's living network, an ensemble of all possible states. But as information arrives, the uncertainty collapses, revealing the single reality that must be. As information enters a black hole, a distant observer retains only its basic properties. At the event horizon, matter falls in with highly structured order, but what escapes appears as a featureless, uniform glow.
In the quantum realm, information is never lost. Through unitary evolution, state relationships are perfectly preserved, sustaining the delicate fabric of quantum data.
At the edge of a black hole, physics as we know it breaks down. Information may be lost forever or preserved in quantum states. This is the ultimate information paradox.
To see the dawn of time, we must look beyond the stars. Here, the cosmos becomes a smooth, glowing sea. This is the cosmic web, the largest structure in nature. Billions of galaxies trace a network of vast filaments and empty voids. We are moving backward through cosmic history. Here, returning to the uniform glow of the early cosmos.
By reversing time, we can witness the cosmos in reverse. The black hole dissolves, returning its mass to the stars, leaving behind the primal nebula that birthed them all.
Before the first stars, the universe was a vast, dark expanse, a nearly uniform sea of primordial gas, slowly drifting in the deep.
Traveling backward in time, we leave the era of galaxies. Deep in the past, the universe becomes a smooth, hot sea of gas. The young universe was a hot, dense plasma, an immersive field with no center and no edge, setting the stage for the release of the first light. At this cosmic dawn, everything was almost perfectly uniform. A single, nearly featureless field of heat and matter. Gravity begins its work. Gravity pulled vast clouds of gas and dark matter together, giving birth to the first generation of stars. Gravity would transform a nearly perfectly smooth early cosmos dominated by black holes, representing a massive increase in gravitational entropy. From a state of perfect order, gravity began to pull matter together, giving birth to the first galaxies and the universe's darkest mysteries. Long before the first stars ignited, the universe was a smooth, boundless expanse, holding in a state of absolute simplicity. Before stars, the universe was a dense, uniform plasma. Tiny variations in density were the seeds of all future structures. This was the dawn of space and time. Our universe began in a highly special state, a tiny region of incredibly low entropy. Ever since, it has been drifting into the vast sea of probability. But this raises a fundamental question. How did it begin in such a precise set of initial conditions? To understand our universe, we must look back to its smooth beginning.
From a smooth and uniform state, gravity pulled matter together, igniting the first stars and vast galaxies, driving the universe toward higher entropy.
Every record costs energy, leaving an irreversible trace, sustaining the arrow of time.
But why was the past so low in entropy?
In the first trillionth of a second, the universe underwent a restrained expansion. Tiny fluctuations stretched into a vast cosmic web, mapping the evolution of space and time.
In a fraction of a second, space itself expanded faster than light, stretching tiny quantum ripples into the seeds of our entire universe. At the hardest boundaries of existence, the fabric of space and time dissolves into pure geometric potential. In this chaotic dispersion, every fragment follows a precise physical law, leaving behind a complex map of random chance. Deep within a single shard of glass lies a chaotic universe of dancing atoms, locking together to create a solid world. This is equilibrium, a single macrostate, compatible with countless arrangements. Heat naturally disperses, it flows from hot to cold. This is the arrow of time, an irreversible process, leading to a state of equilibrium where all difference fades. Every trace tells a story, written in the earth, frozen in stone, and preserved in our own hand. According to Einstein, time is not absolute. Alter its path through space, and its rhythm changes. This clock, moving at high velocity, now records a different history than the one left behind. When hot and cold objects meet, energy disperses into countless new microstates. But at the ultimate edge of a black hole, quantum rules allow even gravity to evaporate.
We travel backward in time, reversing billions of years of cosmic expansion. Galaxies dissolve into clouds of pristine gas, leaving a smooth, glowing sea of pure energy.
Long before the first stars, the universe was a featureless sea of dark matter. But pull by pull, gravity began its slow, inevitable work. Does time flow? Or is it simply an illusion? The laws allow change. Probability gives it a direction. The universe gave it a past. Why does time move forward?